Good morning, everyone. I'm Sergio Casas. Uh, I'm a senior staff research scientist at Waymo in the AI Foundations team. And today I'll be talking about scaling up behavior models for motion forecasting and planning. So I'd like to start with our mission. We want to be the world's most trusted driver. Um, I'll start with an anecdote. I promise this won't be the scientific peak of my talk, but I joined Waymo recently, and I was there for the first time, kind of cautiously excited, riding the Waymo and kind of looking for everything that might happen. It was great. Nothing happened. I took a second ride on the right seat this time, and I was pretty much checking my phone, but maybe at intersections I would check just in busy intersections just in case something happened, and like I guess every good shotgun ready to press the invisible pedal on the right seat. But it was great again. And the third time, really, I basically was coming back from a dinner with a friend, and I fell asleep on the Waymo after like 10 minutes. And I mean, this is only one example, right? But it's just, I was really very impressed with truly how good it works. And I wanted to share that. But I promise we'll have some numbers too. Um, so the first thing I want to say is that this is actually happening at scale. A lot of people don't know. A lot of people I talk with, but we are having right now 250,000 trips. This is without driver per week, which is like about 1 million a month in these 4 cities, basically SF, Phoenix, LA, and Austin. And actually, soon is coming here to Atlanta as well. And what I mentioned before was just my personal anecdote, but the numbers also back that up. In our first 50 million miles, these are from left to right, from most severe to least severe accidents, and we are saving a lot of accidents compared to the average driver in these cities that we operate. This is not comparing to like ride sharing, for example, only, which it's known to have more accidents. This is actually comparing to the average driver, and you can find more in that safety dashboard online. So I wanted to show some very cool examples. You might have seen this one online already. There's a scooter right in front of the Waymo, and it just is able to swerve at the last point. Let's play it again. So this is very hard for humans. I think it requires a very, very attentive human on the wheel, very fast reaction time. Don't getting too panicked about it. So it's a great use case of what we all want autonomous driving to be. This is another example. Let's see as you watch it if you feel like what would you have done in this case, and would you have done better? It is actually very, very tight. So it really needs a last 100 milliseconds maybe reaction time. And yeah, I was also very impressed when I saw it. This is more of a perception thing. There's that object, it's glaring. You actually cannot see, but it's right now you can see at the end. It's going over the line quite a bit. So we need to swerve. I think for a human, when I watch the video, it's kind of hard, at least in the camera, to tell whether it's on the other lane, in our lane or not. But that's not a problem for autonomous driving with LiDARs at least. And this is the last example I'll be showing, and we'll get to the meat of the talk. There's a train on the left. There are the train tracks you can see on the left. This was also shared online, I believe. And you probably haven't seen why we've lane changed, even if you were looking at the camera. But now I ask you to look at the top, which is, or actually I have here a better visual. There are these humans actually crossing from the train tracks, avoiding the train into the road, which are highlighted in yellow. You cannot see them in the camera because it's too dark, but those are LiDAR points and they can see them. And the LiDAR points on the vehicle are in blue. And yeah, this is one advantage of having redundancy in sensors and different sensors. So I really believe the Waymo driver is at least a premier application of embodied AI, if not the premier application of embodied AI. And to be able to be where we are today and to be able to improve, there are these two parts. We need to build the driver, and we need to also validate the driver. My talk today will be about building the driver, and of course, AI is key to both of these. But just for the purpose of time and kind of my expertise, I'll focus on building the driver. And we are here at a motion prediction workshop. And here are some fun and unusual behaviors that you see. Some stray cyclists there doing some wheelies. There's a toddler on the loose in the middle that, to be honest, is very, very hard. It comes at the last moment. It's very cute, but you really need to stop or swerve very quickly. And there's on the right that falling skateboarder that basically was attached to the vehicle in front and loses balance, and yeah, it just falls in the middle of the path. So what are the challenges and opportunities that we want the AI basically to solve? So we want a system ultimately that generalizes to new cities and countries, generalizes to new vehicle platforms and sensor stacks, and generalizes to rare situations. And for this, there are kind of two main advances, recent advances that we want to leverage. First one is word knowledge from pre-trained multimodal LLMs. I won't be talking too much about this one today, but I hope I'm going to be talking about it in upcoming conferences. And this is what I'm going to focus today, it's scale. So scale, it's been shown, right, in language and in many other applications that scaling model size, data sets, training, and inference compute makes a big difference. And I hope I convince you that that is the case for behavior prediction today as well. So there are challenges, though, with scaling up. On the vehicle, we cannot put a massive model. I mean, a lot of optimization can go into it, but ultimately there are limits. It needs to run in real time, for example. The compute is also more limited than in the data center. But we can try to build the most generalizable driver in the data center first. And here we are now limited by vehicle constraints. And there are ways to transfer this to the onboard driver. This can serve as a teacher, offboard teacher, basically, to do distillation for the onboard driver. So the talk today is going to focus on these two aspects of scaling up. We need an architecture that is scalable. On the left, we're going to build on top of MotionLM. And we need also a recipe to scale up training, which we're going to build on top of Chinchilla. So let's talk about the architecture first. So this is a recap of this MotionLM paper that was released in 2023. Trajectories can be seen as sentences in this new language where the vocabulary is the state or motion, basically, and we can think of words. If we think of words, you can see these vectors as they play out in the scene. This is kind of a conversation between the two vehicles are having there. And in practice, we actually don't use deltas, but rather a Verlet wrapper on top of the delta. So you can think of this discretized acceleration is the action space that we are using. And like language, these trajectories have local continuity, meaning that they are smooth and often very correlated one step to the next. And they also have a global context. Usually, you can predict better the future trajectories, let's say, in 7 seconds in the future by looking 4 seconds in the past. Let's say the driver maybe did some erratic behavior, and that helps you tell that this may be an aggressive driver, or they were very cautious at a stop sign, and then you know they are probably going to respect the rules. And of course, the model architecture is going to be a transformer, very similar to that of an LLM. And for more context on the task, we are predicting, for the experiments I'll show later, we are predicting 11 seconds into the future based on 5 seconds of history. So this is sort of the high-level architecture. We have a scene encoder that takes the traffic light states. These are the states of the traffic lights over these past 5 seconds. The road graph, which is static set of polylines basically here, and the history of each agent, which is, all, again, this, the past trajectories of the agents. These are coming from some onboard or offboard perception system with tracking that it's out of scope for the talk. And so basically you have these 2 dimensions, right? You have time and you have agents. And this scene encoder is doing some early fusion, which means we are just doing very light processing for each of these 3 modalities at the beginning, just projecting them into a common embedding space. And then we are concatenating along these 2 sequence dimensions, and we are performing factorized and latent query attention for efficiency. This is really isn't needed for the data center model, but for the, I guess, what I'm sharing today, this is how we did the experiments. And then on the right, There's the motion decoder. So we start with start of sentence kind of token, right? It's just telling this is the start of the sequence. Then we predict the first action. That action gets fed back. This is just basically an autoregressive model. It has a slight variation. When we feed back the actions, so basically you can think of this sequence length as the flattened out number of agents times number of time steps. And basically what we do is that we don't feed back the previous action from any agent to the next token. We'd rather feed the previous action for that agent to the next time we are predicting that agent, basically. So these actions, even though it's a flattened out sequence dimension, we still preserve the meaning, and every token when we are predicting the next action is seeing the previous action of that agent. And that is also accomplished with, this might be more clear. Basically, we are trying to generate these n rollouts, right? N agents over t time steps. And the first equation is showing how basically we are doing this, the modeling of all the time steps in a sequence, the autoregressive part. So we are saying basically that we are factorizing with these per step conditionals, right? And we are predicting a time t based on the previous time step for all the agents. That's what capital A means. And the second equation is talking about how we do this per action conditional, and it's saying that basically we are factorizing it for every agent. So that small a is basically one agent, right? And we are conditioning on the previous action for all agents, meaning that we are assuming conditional independence based on history, which is reasonable for driving, because when you are taking your next action, you don't know what the next action of any of the other drivers around you are. You only know what they did before. So this is an example rollout. This is what we call a joint rollout, which is kind of the natural inference mode of this model that I was just talking about. And you can see the actions from the two modeled agents in blue are consistent. The vehicle essentially is yielding to the pedestrian. And the green agents are just logged agents. They are fed into the encoder as more context, but they are not modeled. They are not predicted. And we can also operate this model in a conditional fashion. What this means is that we are querying based on the future of one agent, in this case the pink agent, and asking what's the motion of the blue agent, the query, the modeled agent, in this case the pedestrian. And basically we are seeing that if we didn't yield, if that vehicle didn't yield, the pedestrian would, or we're predicting it would stop in this rollout. This is possible because, I think I didn't mention it, but here the decoder has causal self-attention. So we are actually not cheating by looking at the future. There are more details, I think, in the Motion LM paper about the importance of this when conditioning. But yeah, that's why we can do this type of querying conditionally. All right, and many of you might be familiar also with marginal prediction, which is we just want the distribution over possible actions for each of the agents instead of the joint rollouts. We can also do that with this model with some post-processing. First, we generate our rollouts. These are joint rollouts for all the agents. And then we can, independently for each agent, cluster them using k-means down to k-modes. So we can pick an arbitrary R, a large number of rollout, and cluster it down to k trajectory predictions per agent. And that looks something like this. Of course, the trajectories are going to intersect. That's fine because these are marginal predictions, right? We are not saying anything about the interactions here or how the scene might roll out jointly. We are just saying these are all the possibilities for each of the agent. Cool. So we have the architecture. Actually, before we move on, I just realized I didn't include any training. But training is trivia here. So the only thing we are doing is teacher forcing. So really, we are passing the previous ground truth actions, right, of every agent and training with a cross entropy over this action space of discretized accelerations. So it's the same as language pre-training, essentially. Cool. And now we can get on to the recipe for scaling up these models. So really, the question we are trying to answer is, if we have a compute budget C, what is the optimal model capacity? And how many tokens or examples do we need to train it? And this is from Chinchilla paper. You can see the optimization equation there is just what I just said. Basically, we are minimizing the loss subject to the fact that the given the parameters and the data set that we are training with, we get these flops during training to satisfy our budget. And one of the ways, actually, they propose many approaches in that paper, but one of the ways they present is these compute optimal models by essentially plotting these curves. So what these curves are is we set a budget. Each of the curves is a compute budget. You can see the numbers there in terms of flops. And then each of the models in the curve is a different set of basically number of parameters, which are varied by some hyperparameters. Like, for example, we keep the ratio between encoder and decoder fixed, but we scale the number of layers. That will give you different parameters. And then if you go more toward the right of any of these curves, you are getting a bigger model, which to be on the same compute band, we basically need to train for less steps. And if you go to the left of any of the curve, you have a smaller model trained for more steps. And you can see for each of these compute bands, there's an optimum. And these are actually all parabolas that we are fitting. And so we can get what we call the compute optimal model for a compute budget by finding the minimum of that parabola. Once you have found those minimums for each of the parabolas, you can plot them in these two charts. So we have flops in the x-axis, or the logarithm of flops. And on the y-axis, we have parameters and we have tokens. Actually, in our case, it's not even tokens. We'll talk about examples because each example has the same fixed number of tokens. But that's kind of a detail. Once we have these compute optimal models plotted here, we can fit that red line, right? In a log-log plot is a line, but it's this basically power law, right, that probably many of you are familiar with. And then this actually has a very powerful implication that we can predict if we have a compute budget that is much bigger than the experiments that we have done this scaling loss analysis with, what is the number of parameters and what is the number of tokens that we should use to maximize the performance under that compute budget? And that's what the green line is on both plots. So in Chinchilla, they basically found that with the same compute budget as this model that probably not many people know called Gopher, you can get a much better performance with a much smaller model. Basically, by doing this compute optimal analysis with scaling laws, they realized the models back in the day in 2022 were too big for the data they were trained with. And by making it way smaller from 280 billion to 70 billion, if you look on the right, Gopher compared to Chinchilla, they were able to achieve a massive gain in this MMLU performance benchmark. And so now we have the architecture, we have the training recipe. We really just have to put them together to basically find these compute optimal models and do some analysis. So the first thing we found is that language modeling and motion forecasting are very, very different in terms of their compute optimal models. The curves look similar, but actually they are very shifted. If you look at the highlighted point in green, for the same number of compute here, 1E21, LLMs, actually, the compute optimal is 50 times bigger than a compute optimal motion forecasting model. And this has been also found in other papers for other tasks, that language is a particular parameter intensive task, maybe because they need to store a lot of facts potentially about the world to be able to answer correctly. Maybe motion is more about the context, and it doesn't have that many rules to be able to predict or to have a good model. That's one hypothesis, but there might be many. Second thing is that open loop metrics are very predictable. So here we are showing those compute optimal models in terms of flops on the x-axis compared to the evaluation loss, and we see they track pretty well with the power law fit. And on the right, we are also seeing it's not just the loss, it's also metrics like mean AD that probably any of you working on motion forecasting are familiar with. The difference between the blue and the right is this irreducible term. So it's whether it's a power law, pure power law, or a power law with this irreducible term. Irreducible term, adding it seems to make a better fit. This has been found in other papers too. There's some curvature. Basically, it's not a straight line in the log-log curve. And this irreducible loss, you can think of as some maybe inherent, basically irreducible term in the task. So for example, here we are doing modeling based on the past trajectories of agents. Those past trajectories of agents might have some errors. And we are now feeding sensor data, for example, in these experiments. So maybe there's some irreducible term coming from that. Maybe it's from the data distribution. There are many hypotheses. This is something we are interested in. But it's, yeah, pretty interesting. And yeah, basically with that irreducible loss term, we get a better fit. And the improvements are qualitatively very obvious. So these are, it's basically almost 2 orders of magnitude bigger model on the right than on the left for the same scene. And you can see the mode coverage is way better just by scaling out the model. Same architecture, same underlying data, just trained for different number of steps, right? For these compute budgets that are on the little pills. And you can see we get the ground truth mode on the right, which we don't on the left, and also all the modes look realistic, which they don't on the left. And beyond scaling training and the model, we can also scale inference. So each of the curves here is a model size, so a model that we've already trained. And on the x-axis, we have inference flops. The way we are using more flops at inference is by essentially producing more rollouts, joint rollouts, and then clustering down to the same K modes. So all these 3 curves, they are apple-to-apple comparison because they are using the same K marginal modes, but they are coming from different number of rollouts. Basically, blue has a lot less rollouts than orange and a lot less than gray. And besides the fact that it's very interesting on itself that more rollouts do better, which makes sense because we are giving more data to the clustering, it's also very interesting that there are these crossover points where it's more efficient at inference to switch to the bigger model and have less rollouts with the bigger model than continue increasing the number of rollouts of the small model. That's what those crossover points mean, which is very cool. I think it's intuitive after the fact, but it's very nice to see. And yeah, this is an example of inference scaling. We basically on the right are having almost 10 times the number of rollouts, and we are able to see similar qualitative improvements to what we saw in scaling the model size at training and the training flops. Basically better mode coverage and more realistic modes. And this is my final slide. We all wonder whether these gains translate to closed loop, and we have a simulator. So we tested this. Basically, we take the motion forecasting model, and we use the actions from the self-driving predicted for the self-driving vehicle as the controls, and then roll out one step of the simulation, get the new environment, run the model again, right? That's how we are doing this experiment. And we see that the scaling laws also apply here, and we also get a good fit by having this power law with irreducible loss. The metric, it's some internal metric, but you can think of a trade-off between progress and safety, lowers better. And we are really showing here that I think this has deep implications that actually improvements in open loop do translate to closed loop, and not only that, they follow similar laws. And with that, thank you everyone for the attention, and I'm happy to take a couple of questions.
Thank you for the talk. I had a question about in the context of learning the distributions, especially when you're like trying to quantify the uncertainty associated with it. Would it be possible to, for example, look at more informed approaches like constraining the model by a PDE or an ODE so that you could reduce the size of the model and instead rely on the underlying physics of the distribution for better rollout performance?
I'd be curious as well. It's not something I've tried, so I can't answer for certain. I suspect it will be hard to match the performance of scaling up models based on the experience and the improvements I've seen. I've spent many of my previous years trying to make better models and kind of on the same budget, and scale is kind of hard to overcome, I guess. And so I would expect you can get some gains by doing something like that. I don't think they will be exclusive with the scaling, so probably scaling and doing that might be a good idea.
Thank you.
Thank you for the talk, Dr. Casas. So in the trajectory estimation model, you mentioned that the token uses acceleration as the unit. So how does the model, do you provide context, like as in positions and velocity too? Is that part of the, like the encoder on the left, or?
Yeah, there's definitely positions. Basically, as part of the encoder, that's the history. I can't remember, these are done with the Waymo Open Motion Dataset spec. I can't remember if there it's provided previous velocities as well, but you can infer those anyway from the positions. Okay. The positions are certainly provided, so that's how the model can tell. And these accelerations are actually on, to make the problem easier, are on agent relative frame. So basically, yeah, with the past history, the model can sort of continue. But then, of course, as you all know, like I mentioned, we are predicting 11 seconds into the future. At some point, the past becomes kind of irrelevant or less relevant. And really the map and the other agents that we are modeling together is what, I guess, discriminates the most towards those long-term forecasts.
Thank you.
Hi, thanks so much for your presentation. So my understanding of like this generative AI type of stuff, and I'm a psychologist, so is that when you have this type of AI, it'll tend towards sort of what's the norm and start to exclude cases that aren't as much the norm. So I was wondering, how do you train cases that are less common? Like, for example, wheelchair users are 36% more likely to die as pedestrians because of cars running into them. So how do you make sure that cases like that are also trained into the model?
Yeah, thank you. I think maybe first from a kind of more statistical perspective, the regression to the mean is more of an issue when we have regression-based models. So here we are discretizing acceleration and then classifying over those classification bins of acceleration, which means that really the model is inherently multimodal, and we are not really having this issue of regressing to the mean. That's one aspect. And then you also touch on kind of rare cases in terms of rare objects. These are out of the scope of this analysis. This was done on cyclists, pedestrians, and vehicles. I think these type of methods, if you have enough data, they're great. Otherwise, you usually have, basically what I'm describing is by no means the full system. There are other systems that are more tailored towards handling cases like that. Usually less so based on labels or previous perception inputs, but more so based on the raw sensor data. Yeah.
Thank you.
Thank you for the talk. So I had a general question, and when we are talking about state and action in this case, what is the state? Is it whatever happening in front of the car, or it considers the surrounding as well, especially like in the cases that the car was slamming on the brakes, it might be a near collision scenario if the car behind it is just running very fast. So I was
Oh, I see what you mean. That you're asking about which parts of the scene are considered essentially?
as the state, yeah.
Sorry, as what?
As the state, when we are considering the state actions.
The state we are modeling is very simple here. It's just those discrete actions. That's what we are predicting. But the context, those discrete actions are predicted at a high frequency, in this case 10 hertz. And I think what you were saying, for example, a vehicle behind, that's handled by the context itself. So in the context, in the encoder, we have many agents, basically all the perception outputs. And we are modeling a finite set of agents. In this case, just for the analysis, it's 8. So the 8 nearest agents around SDC is what is actually being modeled. Modeled meaning predicted into the future. We still have as input all the perceived agents as part of the encoder.
Thank you.
Hey, so you started your talk by talking about all of these out of distribution types of edge cases, and then you've told us about prediction. how are you balancing your actions so that you're considering both the prediction and while also being aware of these non-traditional cases?
Yeah, I think for the non-traditional cases, like for example, if I think of that bike on the wheelie, I think they are well handled by. So basically, we have this acceleration action space, and it's pretty high frequency. So the integrals of that acceleration changing very quickly, right, can give you very fast changing positions, which I think would handle those cases. Um, yeah.
Hi. Thank you for the talk. Sorry, I missed a little bit of the beginning, but you had mentioned you were using discrete actions. I was wondering if this would be like just quantized values of like a discretized range, or if you also maybe considered trying like some predefined like discretized vocabulary over some kind of like a latent vocabulary.
Yeah, these are all things the team has considered. In the study, the results I talked about is just binning over those accelerations. It's actually, to be more concrete, is binning on the deltas, so basically velocities, right?
Okay.
And then the actions are essentially predicted as this Verlet wrapper, which is just the difference in deltas. So the bidding happens at the delta level, but we are predicting the difference between the deltas, discretized deltas, which is another discretized action space. That's what we are doing, but it's basically discretized acceleration at a high level, and we are just bidding. We also, I think the team tried also other strategies like BQVAE and other things. I think they were more complex and they didn't really yield improvements, at least at scale. So we prioritize these like simpler action space. Yeah.
Yeah. Thanks.